A Class A power amplifier designed with transformer is discussed in this example. The circuit is implemented with one pair of Darlington BJT bipolar junction transistor NPN type, one N-to-1 ratio ideal transformer, and we want to deliver to a load of 6.25 ohm, a power target of 2 watts, and supply voltage at the input of the circuit is 20 volt, and the input signal is assumed to be an AC signal sinusoidal as shown here. The question is how this circuit is working, and also how can we design the circuit in terms of finding the proper value for the bias components, let's say R1, R2, and also RE, and also the number of turns for the transformer, and a proper choice of Darlington transistor in terms of the tolerance for voltage and current, so that we achieve this 2 watt power delivery target given the 20 volt supply. So to answer these questions, I need to do the DC and AC analysis of this Class A power amplifier quickly, and also it's important to notice that given the ideal N-to-1 ratio transformer, the observed primary impedance would be, which is referred to as R'(L), is simply R'(L) equal to N square, which N is the turn ratio for the ideal transformer, times the RL, which is the impedance, the target resistance that we are supposed to deliver the 2 watt power to. This is just coming from the properties of ideal transformer, in which the voltage of the primary, which I'm going to show in different colors. So let's say this is the voltage of primary plus minus V1, given the polarity indicated for transformer. This is the voltage of this secondary here, and the relationship between V1 and V2 given the N-to-1 ratio as shown is just V1 is N times V2, and I1, if the I1 is basically this current, is equal to 1 over N times I2. Hence, we get this relationship for the R'(L) observed from perspective of primary as a function of RL in the secondary of the transformer. Okay, so the other important thing is let's do a quick DC analysis. So for a quick DC analysis, it's important to notice that we have a 20 volt supply, so that 20 volt is right here. And then we can write a KVL, or Kirchhoff voltage law, which basically says the sum of all voltage drop across this branch should be equal to 20 volt, because the other side we have ground. What do we have? We have a primary that is ideal transformer. It has 0 impedance DC-wise, so there is no DC voltage drop across this guy. So the only DC voltage drop we have is plus minus VCE of collector emitter of Darlington transistor, bipolar junction transistor, and then we have, because of the DC current that is passing through the resistor RE, we also have the plus minus RE times IC DC voltage drop across RE. Therefore, I can write, again, a KVL basically, Kirchhoff voltage law. So the sum of all voltage drop should be equal to VCC. So VCC equal to 20 volt, this is what I refer to as supply, or VCC, is equal to VCE of the BJT transistor plus RE times IC. Okay, so if I'm supposed to just draw this, and let's put it this way. So I'm going to move this guy. I'm going to move this guy to here. Let me put it here. That's a better drawing. So if I move this guy here, then I can draw the DC line, which is basically just this line. I can draw it like this. So on the y-axis, I have the current IC. On the x-axis, I have the voltage of collector emitter of transistor. So collector emitter of transistor, and then I have the current of collector. So if I draw the, let's say, DC current, or DC IV characteristic for DC, it would be like this. And this is the point that IC is hypothetically 0. So when this is 0, VC is simply equal to VCC, 20 volt. So as a result, I have at this point just VCC. And then when I am here, it's when VCE hypothetically is 0. Of course, the minimum VCE saturation of the transistor, which is 0.2 volt or higher. So therefore, hypothetically, this node here is simply just VCC, or 20 volt divided by RE. RE is usually a very small resistor, but relatively should be able to tolerate sizable power. Now, for the AC analysis, so this is just the line for the DC analysis, and this tangent is simply RE. Now, for the AC analysis, I'm going to write it here. So for AC analysis, what do we have? So the bypass gap here would actually result in this node AC bias to be grounded. The bypass gap here would actually also result in emitter of the Darlington BJT transistor to be AC wise grounded. So the two AC voltage drop, one V1 AC across the primary of the transformer, and with the polarity that is shown plus minus, and the VCE AC, the sum of these two should be 0 because they are between two ground nodes AC wise. So I can write V1 plus VCE AC of the BJT transistor, Darlington transistor, should be equal to 0. But then V1 is simply the current I1 that I showed you before times the observed R prime L at the primary. So this one is simply R prime L times IC of AC current of transistor. So I can say VCE therefore is minus R prime L, which is this value of course, times IC. So if I just show this one, let's say, let me change the color so that it's obvious which one I'm talking about. So this one, let me use let's say the green color for, and then if I draw that, it looks like I have this line. So here is AC IV line, so I have, let's say, this line roughly. So this bias point, let me just show it in a better fashion. This bias point is in a practical design, is very close to VCC. So this VCEQ, the quiescent collector emitter voltage of the Darlington transistor, in practice will be very close to VCC. We can make the assumption these are roughly equal to each other. We design in such a way that that becomes practically true. And then we also have, for the quiescent point or the bias point of transistor, we also have this value, ICQ, or the collector current for at the DC or bias point, the quiescent current, and then this node naturally becomes 2 times ICQ. For the proper design, we are trying to maximize the use case of transistors. So basically what it means, there is a DC current ICQ that is passing through transistor via proper bias. Now during the AC, so when this signal at input is doing the AC oscillation, then the transistor would experience an AC current that in the maximum amount can counteract the DC current, basically resulting in total current spontaneously or momentarily for transistor to be equal to 0 when exactly AC current cancel out the DC current in the best design. So what I'm trying to say is, when AC current shown here is like this, so look at the polarity of the plus minus V1 AC bias. So when we have a negative AC current, the peak negative value of the AC current can be just negative ICQ. So basically cancel out the DC. And then on the other hand, it's a symmetric AC current, so on the other hand can be plus ICQ. So when it is plus, then we have effectively double ICQ passing through transistor. So what I'm trying to say is the Darlington transistor selected should be able to tolerate up to 2 times ICQ, basically up to this value. So this level is going to be the max level that current that transistor should be able to tolerate. So I'm going to write it here. The current max for transistor, for Darlington BJT transistor, should be basically greater than or equal, so greater than or equal 2 times ICQ. So that's one requirement we're going to keep. At the same time, the quiescent voltage VCE is roughly equal to VCC, which is 20 volt in this design, the supply voltage. But now here's the problem. As we are doing this sort of a swing, AC swing for the output AC current, so this is AC current at the output, or at primary of the transformer. So output meaning at primary of transformer. Then what happens? Transformer. Then what happens is the voltage of the collector compared to emitter of the transistor again also experience double the VCQ, because what we have is at lowest level the collector voltage can get theoretically down to emitter voltage, but in practice down to saturation. So I'm going to show it like this. So here is the VCE of transistor in AC mode. So we have, let's say, the VCQ center point, and then we have down the total voltage of the collector emitter, and then we have down to let's say theoretically 0 but practically 0.2, so basically VCE sat. So VCE saturation of the transistor, which is 0.2 volt roughly, or a bit higher for power transistors. And then on top, but let's make the assumption that this is practically 0 given the size of 20 volt supply or VCC. And on the other side we have, so we go 20 volt down, we go 20 volt up. So effectively we have, and the center is 20, so we have up to 40 volt max VCE that can happen for transistor. All I'm trying to say is the transistor should be able to tolerate VCE collector, basically the breakdown voltage for transistor, which we write it as BD, or breakdown voltage of the collector emitter, should be greater than or equal 2 times VCC, which means 40 volt at least. That's also another requirement we have. So with these requirements in mind, now we can do the analysis. So we know from this that in the best power delivery mode, we have this sort of AC voltage at the primary of transformer and this sort of AC current at the primary of transformer. So given this sort of AC, we can just say, and given that the transformer is ideal transformer, meaning that there is no power loss. So if we want 2 watt in the secondary delivered to RL, the 2 watt should be in the primary as well. So I can therefore say, at the primary of this transformer, I can say, at the primary of transformer in this circuit, in this Class A power amplifier, I can say the target power is 2 watts, and hence is 1/2. It's AC power, so we know that the power is simply V, let's say V peak of AC, so VAC peak squared divided by R prime L, which is the resistor observed in the primary. So now we have everything. We now have 2 watt equal to 1/2, and it's 20 volt as we discussed for peak to peak, so low peak to high peak, so it's 2 times 20, so the peak is 20, and therefore I can write 20 times 20 squared, and then we have R prime L. So when we do this, we can say R prime L is effectively 400 divided by 400 ohm, and since R prime L, I'm going to write it here, so this is one outcome. Since R prime L is equal to N square RL, and RL is 6 point, so is equal to N square times 6.25 ohm. Here we get n square, given that r prime L is 100, L square is 16, which means n should be equal to 4 turns. So we found the right number of turns for the ideal transformer as well. Now, the next step is, of course, finding just the max, the current, the peak of the current, which is ICQ. So I can say for at the primary again of this transformer, there is a simple relationship between voltage peak of AC and the current using Ohm law. So using Ohm's law, we have IAC peak, R prime L, VAC peak equal to R prime L times IAC peak. So in this case, we have 20 volt equal to, so R prime L is 100, as we found here, 100 ohm times IAC peak at the primary. So we get that IAC peak, which is ICQ as well, because we observe and discuss that the peak of the current can be as much as ICQ, or the current of the bias for the transistor. So is IAC peak is equal to 20 volt divided by 100 ohm is 0.2 amp, or basically 200 milliamp. So we found the ICQ. Okay, so we found the number of turns, and we found also the ICQ. So in this case, I would say pick the transistor. So given what we found here, and given the requirement we discussed for the current and the breakdown voltage of collector emitter for transistor, I can say, therefore I can say, pick the transistor, pick a Darlington transistor such that we have the max current that it can tolerate greater than or equal 2 times ICQ in this case, which is 2 times 200 milliamp. So it should be greater than or equal 400 milliamp, the tolerance for the max current. And also breakdown voltage of collector emitter should be greater than or equal 2 times VCC, which is 40 volt. And the power delivery also is important. So you can see that we have from 20 volt, we have a DC bias of a DC current of, say, ICQ of at this node, ICQ of 0.2. So power, let's say from supply, taken from supply, VCC 20 volt is simply, we have VCC, so I'm going to write it here, P of supply, or P, let's say you can write it P of supply, or PCC here, is equal to value of supply times the ICQ, which is equal to 20 volt times 0.2 amp, which is 4 watts. So that is power supply. Why is it important? Well, when there is no input V in, basically when V in is 0, there is no power delivered to the output. All the power from supply should be then consumed by the Darlington transistor, because that's the dominant consumer. So in class A, when there is no input, we have the maximum waste. So when 0 input, then all 4 watt is burned in Darlington transistor. So therefore, as a result, the transistor should have a P, let's say transistor max, that is greater than, let's say 4 watt. So greater than 4 watt in this circuit. these are the spec for transistors. As an example, I have just one example here. There are many ways to find the proper Darlington transistor. There are many providers. You can search in Mauser or in other, let's say, DigiKey, but one example is from On Semiconductor. onsemi, this let's say Darlington transistor is actually a little bit over design even, but it's a very good one. As you can see, there is a part number for NPN and also there is a part number for PNP. So in this case, we care about the MJE270 from the onsemi.com. So this Darlington transistor has a tolerance for the max VCE of, there you go, 100 volt, which is more than what we need here. And also it can tolerate the 15 watts, assuming the proper, let's say, heatsink. Otherwise, we need to be careful. So when you read the spec, be careful that what sort of a requirement need to be satisfied so that the transistor is not burned. Because for 15 watt, we need to make sure that the power, let's say the temperature of the collector at 25 C, so not the ambient temperature. So we need to be careful that proper heatsink is there. But if a proper heatsink is there, then this Darlington transistor can tolerate 15 watt. And then the current is definitely sustained. This collector current continuous of 2 amp, which is much more than what we need. And also, as you can see, that HFE of transistor is typical minimum 1500. So an HFE of 2000 is very reasonable to be assumed from this transistor. So beta HFE of, let's say, 1500, which, for example, let's say 2000 beta, is nothing strange for this transistor. So this is an example. Now, why does this matter? Well, the next step to find the DC component is actually dependent on the properties of the Darlington transistor we select. So in this case, if I go back, for this approximation, the only requirement is RE. So I'm going to put it here. It's a practical part of the design. So RE, or the resistor at the emitter of transistor, Darlington transistor, should be considerably less than R prime L, or basically considerably less than N square times RL. So we designed the Class A amplifier such that this is satisfied, and therefore we benefit from this approximation that VCQ is practically just VCC. Okay, so to achieve that, take a look at the DC current that we found. So the DC current of this design is 0.2 amp or 200 milliamp. I am going to select the value of, let's say, RE, such that the voltage drop across RE is just very small. So for instance, I am going to select it to be just, there you go. So I am going to select RE. So let's say set RE to, just as an example, 0.5 ohm. It can be 1 ohm, it doesn't matter. So as an example, let's say 0.5 ohm. And then we get voltage across RE is the DC voltage is just ICQ, the current of the DC current of the Darlington transistor, times the RE. So in this case will be 0.2 amp times 0.5 ohm is just simply 0.1 volt. So what we have is, DC wise, we have a 0.1 volt drop across this RE, and then for the Darlington pair we have 2 VBE, so 0.7 and then 0.7, so 1.4, and then we have KVL, we have 2 let's say PN junction voltage drop, so 2 times 0.7 plus 0.1 is 1.5 volt DC here. Okay, so the only requirement is we want practically this R1, R2 series to be effectively series. So basically the current of the base of the Darlington transistor I base should be considerably less than the current, the DC bias current passing through this branch IR. So that's the only requirement. So let's set, so I'm going to set it here, IR IR1 equal to IR2. So I'm going to put it this way. IR1, let's say, should be roughly equal to IR2, and they should be much larger than I base of the Darlington transistor. So to achieve this, I'm going to set, given that beta is roughly 2000, so ICQ is 2.2 amp or 200 milliamp. Beta is roughly 2000 for the Darlington, or HFE is roughly, the current gain of Darlington transistor is roughly 2000, and therefore I base is simply ICQ divided by beta, which is 200 milliamp divided by 2000, which means we are dealing with very small 0.1 milliamp current at the base of Darlington transistor. So to just make sense out of the whole thing, let's make R1 plus R2 roughly on the order of 25, let's say, kilo ohm. And as a result, if I set it like this, I get IR1 plus R2. So this means this is satisfied. IR1 R2 is simply VCC or V supply divided by R1 plus R2 in series, and we get 20 volt divided by 25K. Or let's say we can set it 50K. It doesn't matter. So we can set it 50K. These are kind of a design choices we can make. So if we do so, then what we get is just a matter of, let's say, 40 milliamp. I think so. So we get, I think we get, let me just make sure I'm not making a mistake here. So if it is, let's say it's 5 kilo ohm. My bad. Let's say it's 5 kilo ohm, so that we get large enough. So if we set it to 5 kilo ohm, now it's better. If you set it to 5 kilo ohm, then 20 divided by 5K, what we get is 40 milliamp. So it's going 4 milliamp. There you go. So that current is 40 times. So 40 times I base. So we can assume, therefore, this current is much larger than this. We are satisfying this requirement, basically. So that's what I wanted to say about that, which is a good thing. 4 milliamp here is the current. Now we want 1.5 at the base, so we can find R1 and R2 as well. So what I can say is, I can say I want voltage at the base of Darlington transistor to be 1.5 volt. It's and R1 and R2 are basically in series. Practically. So basically it means voltage at the base is VCC times R2 divided by R1 plus R2, voltage division between these two resistors. And we know the sum is 5K. We just set it intentionally to be 5K. So as a result, 1.5 is equal to 20 volt times R2 divided by 5K. So from here we can find that R2 is simply equal to, so we have 20 divided by 5, it's just 1.5 divided by 4K. So 1.5, let's say, K divided by 4. So that's the value of R2. And then let me just make sure that I'm not missing something. Over here I said 5K. 20 divided by 5K is 4 milliamp. That's exactly good. So this would be the value of R2, and then we can find R1 as well. So R1 and R2, the sum should be 5K. We found R2, therefore we can find R1 as well. So this is the process through which we can find the value of all components, and then as I discussed, we can also properly select a good Darlington transistor given the requirements for the transistor in terms of maximum current and voltage and power that transistor needs to satisfy. I hope that this example is helpful in terms of showing how a Class A power amplifier can be designed with transformer. Thanks for watching.